finish. So, and there are two things I want to, three blackboards I want to present to conclude the discussion. Maybe this is not what yeah. I wanted to reutilize this, but this was stimulated by the question of some of you. So ask questions, please. Try to not to be, I don't know, maybe sometimes you don't ask questions because you don't interested, sometimes you don't ask questions because you think they may be silly. There are no silly questions, there are only silly answers. Okay? And often I give silly answers. So the picture, the RG flow picture I presented yesterday may come confusing because I said RG, normalization group, but I didn't do any loops. So in what sense was I speaking? Well, I was speaking in the following sense. As I said, there was this scale lambda, which for me is truly a physical scale. Okay? And when you normalize theory, you introduce a normalization scale, which is not a physical scale, which you the scale is introduced for calculational purposes to make to organize your computation in a way such that it converges better. Okay, so the scale I start with is a physical scale, so it's not a normalization scale, and or you could view it as the only normalization scale that I have because I've integrated out everything about those scales. And at this scale, our theory emerges and it has everything, all the couplings. And let me identify three couplings that essentially contain all the information for the scalar theory we were dealing with. The quartic, the quintic, and the cubic. Okay? Well, it's clear why. This is dimensionless, this is dimension -1, this is dimension +1, okay? There are very few couplings of positive dimensions. There are finitely many of them. There are infinitely many couplings of negative dimension, okay? This coupling has an inverse power of lambda, okay? If you write it properly, this G5 gets some coefficient, 1/lambda, okay? Sometimes I write the lambda, sometimes I don't, okay? Now, by simple dimensional analysis, if you can easily conclude that when you compute the quantity, typical quantity is a scattering amplitude at energies that are below lambda, okay, and let's say above the ultimate infrared cutoff, it could be the mass, okay. The effect of this coupling is simply determined by in the series that defines your observables by multiplying it by the energy scale that constructs a dimensionless quantity. All series are series in dimensionless quantities. So in particular, G5 will always appear with objects, expressions that scale linearly with the energy. G4 will appear by itself, and G3 will appear like that. Okay, and this was already enough, okay, to get at first sight what's going on. Okay, that all the couplings of negative dimension become unimportant, or their effect is suppressed as when you go towards lower energies. The dimension 4 are essentially stable, they remain equally important or equally unimportant, and the couplings of positive dimension are unimportant to start with, and eventually they can become very important. In fact, they can completely discombobulate the structure to get to a new regime when this can become order 1. This was the picture, if you want, at the classical level. So what is the picture at the quantum level? I already said that there are the most convenient way, if you compute quantum effects the computation of quantum effects is a question of organizing yourself. Okay, if you compute it simply by cutting off loops, virtuality at the scale lambda, which is the standard, the most obvious way to do it, then it turns out that you have to do a clever rearrangement or redefinition of your couplings to have it written in a convenient manner, in a manner that is manifestly well organized. Dimensional organization is actually doing that for you. You can be, dimensional organization is, we invent things in order to do computation in the dumbest possible way without having to think what we're doing, we just compute, okay? And in dimensional organization, if you apply dimensional organization, things are organized in such a way that this picture gets only corrected by logarithmic effects, okay? So wherever this appears, and all the other coupling appear, what they can appear is logs, in addition, logs of E over lambda, okay? And this, okay, these are precisely what you would call the RG flow, okay? Is the additional mild dependence influence, which is induced by these quantum effects. But of course, for couplings that have dimension higher than 4, this is a mild effect compared to the scale dependence that you already had at the classical level. Similarly here instead, for the couplings of dimension 4, this is the only effect that you have, dependence, and this is essentially the subject of 90% or 95% of the randomization program in quantum field theory that you have learned in classes, okay? Normally focus here, and what the basic story there is that these logarithmic effects can be compressed, their effect can be absorbed into a so-called running coupling, okay, which is the original coupling plus coefficients, okay, here, effects that go like the log, and another coefficient, SU1, SU2, G4 cubed, log square, E over lambda, and so on and so forth, okay? And the interesting thing of all this is that you can write this dependence on E in terms of differential equation, is the RG equation. Which you can expand as a power series, corresponding to the various loops. And the reason for that, well, the reason for that, when you do when you carry out the ordinary school type organization program, well, you add counter term, you do this, you do that, and then you use the fact that the Lagrangian, that the results should be dependent on this normalization scale that appears in your computation, and from that you deduce this. The physical reason is that seeing by doing the computations a la Wilson, but this is not the way we do it because it's not technically convenient, it's very cumbersome to do it this way. But the basic statement is that what is this running coupling is simply the coefficient G4 that you would have in your effective Lagrangian if you had gone on integrating out. Because if you're doing experiments at these low energies, again, all the virtual nodes that are at these scales, you will not see them, so you can integrate them out. And then you can define yet another effective Lagrangian where you integrate it out down to some scale E star, which is perhaps not much bigger than the scale energy, perhaps a factor of 100 bigger than the scale where you do the experiments, so that, and in this process of integrating out, you essentially are accounting for all these logarithmic, the good part of this logarithmic effect that comes from quantum fluctuations at these shorter distances. But I should say, the course is not aiming at clarifying the technicalities of normalization, otherwise it would take a week to do that properly. So, but you are encouraged to ask questions, okay, if things are not clear. So, as I said, it's a meta course. It's like a course. It's parasitic sitting on the efforts of other teachers that you had before. Okay, it's just a parasitic course if you want. And as I said, so, okay, that's it, okay. So I hope this more or less clarifies things, or make them even more unclear, perhaps. That's always the risk, we go one direction of that. So this picture that I said, that I presented, where you have a certain scale, UV scale, when you start, when your theory emerges for some principle, unspecified ultraviolet physics, and then there is a, for some reason, if for some reason there is a large separation of scales, which can be associated with the fact that the low dimension operators, for some reasons that we may want to investigate, are very small, so that it takes to go down, down, down in energy before these guys start becoming important, okay, and that you get into a new regime. This is what we encounter. The situation is what we encounter in particle physics. Concretely, let me give you an example. So we have in particle physics a scale, which is the W and Z mass. Okay, this is the weak scale. Okay, this is the scale at which several of the particles in the standard model acquire mass: the W, the Z, the Higgs, and in fact the top also. Okay, let me just put it this way: and W is the scale around 100 GeV. We know precisely what, rather precisely. Okay, we're not saying precisely what the theory is there. Okay, and however, okay, when you study lower scales, it's not necessary to keep all the degrees of freedom you have there, so you integrate them out. And what you obtain here, it's a theory which is known as QCD. Okay, there is QCD plus, okay, there is the photon, and plus the leptons and neutrinos. But and their interaction are just their masses, and at leading order, of course, you can refine it. And the leading interactions are the QCD gauge coupling and the QED gauge coupling. Of course, the QCD gauge coupling starts already bigger than the QED gauge coupling, so you can think of an approximation where you neglect the electromagnetic gauge coupling. So what you have is just QCD, and QCD is a theory where you focus only on the particles that carry color. And here the Lagrangian consists of the gluon kinetic term, the quark kinetic terms. In first approximation, well, okay, there are 5 quarks. Let's think of, for a moment, of an idealistic world where all the quark masses are 0, just for the sake of it. Okay, and of course, in reality, there is the bottom. In reality, there are more mass scales. There's the bottom mass and the Charles mass scale. But for a moment, let's assume we have 3 flavors: only the up, the down, and the strange. So there are these quarks, and these quarks, for some reason, are very light. So you have simply that, and this is the leading order Lagrangian, and the interaction that appears here, although it's hidden inside the covariant derivative, is a dimensionless coupling. It's the strong coupling, okay? And on top of that, you will have interactions that are suppressed by 1 over NW squared, okay? And these are the weak interactions which mediate some processes, for instance, beta decay, that do not exist in this theory. So in some respects, if you want to understand neutral decay, neutral decay happens at first order from these interactions. So even though they are very weak, because they're suppressed by a mass scale, in some cases they're important. Anyway, but this is a series in this. So that's an example where the scale lambda, all that I want to say here is that this is an example where the scale lambda is a W, okay, and W is the scale lambda. Now, what happens in this theory? In this theory, as I presented it, there is no interaction of positive classical dimension. There's no coupling that has positive classical dimension. The lowest dimension coupling is the strong coupling, the gauge coupling that is classically dimension 0. Okay, so all the effect, the leading effect in the evolution from this scale down is due to the logarithmic slow initially logarithmic evolution of this coupling. Okay? And as you know very well, this evolution makes this coupling grow in the infrared. Okay? And at a certain point, around at energies or around, so this is energies, this is a W, and this is about 1 GeV. Around this energy, this coupling G star becomes, GS becomes of order 4 pi, becomes or large, okay? As large, so large that the perturbative expansion breaks down. Now here, we cannot assess what happens in perturbation theory, so this is why there is a highly developed area of high energy physics, which is lattice gauge theories, that is mainly focused on understanding, deriving what happens below the scale from prime principle, purely starting from this coupling. Okay? But again, so what happens here, it's yet another version. In fact, let me go a little bit higher because I cannot go to hell. Okay, let's do it like this. This is lambda QCD. It's about 1 GeV. So here, again, now you have, so you start from the W scale where all the higher dimensional operators associated with electronic physics are important, and as you go down with energy, their effects, the effects of all these other guys goes like E over NW. So it starts going down. Okay, it starts going down. Then there is an intermediate regime, let's say between, let's say around in the middle, okay, with 50 to 5 GeV, where essentially the dependence on energy is a cruising, is a slow cruising, okay? The theory is approximately scale invariant because the evolution of GS is slow. And as you approach 1 GeV, this evolution grows fast, okay? GS starts, and this is energy. And then at a certain point around 1 GeV, this becomes of order 4 pi. And this is where you have all the phenomenon of confinement, the chiral symmetry breaking. And so what happens, so a new scale is formed, and below this scale, a new theory emerges, okay, which is written in terms of different degrees of freedom, okay, and in particular, the only light degrees of freedom that emerge here are the pions, okay, that are light for reason related to symmetry, Goldstone theorems, and they are Goldstone boson of the approximate, I mean, in the limit where the mass is zero, they are really massless particles. The Goldstone boson is 2 times with chiral symmetry. But again, the story starts all over again. You start from here, and what you have here, you have a pion Lagrangian, and pion Lagrangian is a Lagrangian that describes the interaction of Goldstone boson. Goldstone bosons have to decouple when their energy is zero, so all the interaction terms in the Lagrangian will involve some derivatives in such a way that when the derivative is zero, which is to say the momentum where the energy is zero, the interaction turns off. So you have terms that start like the kinetic term, and then you don't have this. You don't have, because this does not have any derivative, you only have interaction with derivative. And you can easily see with scalars, the lead interaction with derivatives is an interaction of this type, let's say pi d pi mu square. And this has dimension 6, so we'll have some scale, lambda, here below, and what is the scale is simply lambda QCD. And then there are even higher orders in 1 over lambda. So the game starts all over again, okay? The peculiarity of this theory is that this theory has a leading term, which is the kinetic term, has dimension 4. It has nothing at dimension, there's no coupling of dimension 0, and all the couplings are, so to say, irrelevant. So that if the quarks were really massless, and the pion, so that the pion is really completely exactly massless, then this theory would run down to, you could run it down to energies approaching 0, down to 0, at which it behaves like a free theory, exactly free theory. But again, it is the same story. And then, well, the basic question of particle physics is what's going on here, okay, and then we will get back to there tomorrow and the day after. But one of the possibilities is that was studied in the 70s and 80s, is that there is yet another layer, which is the gut scale, okay, which is about, this scale is somewhere in 10 to the 15, 10 to the 16, depends. let's not get into the issue. And again, something happens here. There are some particles that acquire mass, and the picture was that below this scale, what emerges is just the standard model, in all its glory, okay, with all its field and couplings, okay. And what is the standard model? So the standard model appears, but it will appear the way you know it on the CERN t-shirt, plus other effects that go like powers of 1 over n something here, 1 over n gut square, and so on and so forth. It will appear again as a series in inverse power of this other mass scale. Now, the standard model Lagrangian, in this regime, not at this scale, here there is a huge separation of scales, and it's a question to understand the origin and the separation. In fact, it's the essence of this course. But in this broad regime, which we would call the desert, nothing really happens. Okay, what happens is that these initial, these terms, that infinite tower of operators of dimension higher than 4 with coupling of negative dimension, slowly become irrelevant. Okay, their impact is suppressed by, if you start going to low energies, their impact is suppressed by E over m gut, and as soon as the energy, let's say, is 10 to the 15, 10 to the 16, you go down, if you're a magnitude, this becomes irrelevant, and all the story is in the hands of the t-shirt Lagrangian, which, to forget the Higgs mass, consists of the kinetic term, which are exactly scale invariant, if you want. They're just they describe free particles, plus the interaction terms, which are the gauge, the UCAV, and all that, which run very, very slowly. So again, this Lagrangian, this regime is approximately scale invariant. Okay, so because it consists of the free field theory, which is scale invariant, plus couplings of dimension 4, which are classically scale invariant, and if they are weak, they only evolve by this quantum effect that you can compute with loops, and the evolution is, however, slow as long as the coupling is weak. So again, so the picture is that the picture of physics is that you have this like milestones, okay, where the regime changes, okay, and in various situations, and in condensed matter we have several examples, this the situation that can, the situation where you can describe physics with few parameters is always the one where you have a big separation, okay, and the big separation of scales, okay, where just below the higher scale, the whole tower of operators that carries the information of what happened at shorter distances, the couples, and you have only a few couplings. Okay? And on top of that, in this window between these scale separations, which we can call desert, the dynamics is approximately scale invariant. Okay? So this is the recurrent picture. Okay? And so essentially, physics viewed this way is a set of steps from one tool boot to the next, okay, between which you just cruise slowly and nothing really dramatic happens. And the drama happens at this point where, and you can see it both from approaching from above and from below. Here, when you approach from above, what you see is that this coupling is becoming strong. Okay? So something happens, the dynamic changes. But you can also see that from below. From below, when the energy grows here, you see the coupling of this other description becoming strong precisely, and the description breaking down exactly at the same scale. And similarly here, okay, at all stages, it's something like that. Okay, okay, very good. Any questions on this? Please.
So if I wanted to do physics at precisely 1 GeV, right, precisely at lambda QCD, can you write down a transition Lagrangian?
No, the transition Lagrangian would have, I mean, if you really want to integrate out everything and write a Lagrangian here, that Lagrangian would have infinitely many terms. Of course, they're all connected. They are all function of one parameter. Okay?
So
They're all connected, okay?
Is it essentially just not possible to do physics at lambda QCD?
No, it's possible. You define your Lagrangian much shorter distances. It's like doing chemistry otherwise. Okay, so chemistry is doing physics without knowing what happens inside, right, essentially. You know how things bind, you have a lot of data, okay? For every new atom or new compound that you can think of, you measure how they bind, and then but you don't have a reductionistic point of view where you compute those things in terms of a few parameters. But that is possible because we know that atoms are made of protons and electrons, and with that microscopic description, we can reproduce all those data. Of course, it's an effort of computation, okay? Is this clear? With a computer.
Yeah.
So, the input of your computation is always the microscopic description. Okay, is this clear? The description becomes simple. In other words, people like me who do computation on a piece of paper are totally useless here. I can be useful here. Well, here is weakly coupled. Here, it's easier, okay? Even if because again, we have the complete theory here, but on top of that, the theory there is weakly coupled. So we just use the microscopic description of the standard model and everything is fine. Okay, in other words, the transition, I should have said, the transition from here to here is not as dramatic as the transition from here to here. The transition from here to here is simply that some particles have acquired a mass and you can integrate them out. But there are no bound state forming here. The particle, the fields that you have here, okay, that's here are the same that you have here. Okay, you don't have. While here the fields that matter here are composite fields in terms of the field that you have. So it's truly a different set of variables. I don't know whether this is. Maybe this is not making it clear. Maybe somebody can chip in. I don't know.
Well, you can use lattice QCD.
No, I said, yeah. No, yeah. Here you lose lattice. But I said, yeah. Here you lose lattice QCD, and lattice QCD is a numerical computation, computational method. But the only input, if you're clever and if you have enough money, is the QCD coupling. Okay. Then there are a lot of other spurious effects which you try to get rid of in this approximation.
To do lattice QCD, you still need a Lagrangian, right? Or
yeah, you need a Lagrangian defined on this. In other words, in lattice QCD, let's say ideally, how you do lattice QCD? The ideal lattice QCD, the beautiful lattice QCD. We have a lot of money. We approximate space-time on a lattice, on a grid that has as a length, which is 1/50G. Let's say maybe 20. Okay, which is a factor of 20, 50 smaller than the scale where things become messy. So it's 50 to the 4th point. Okay, let's see how many. Okay, and so in this discrete space-time, you write down an effective action for discrete for the field that live on this discrete point. Okay.
So writing down the effective, because you said if we write out lambda QCD, right, a Lagrangian is infinitely many terms that are all
this Hamiltonian that you, or Lagrangian, this Lagrangian construct on this. So this lattice length here.
So will the lattice length makes only finitely many important, or because
no,
obviously
they are
input
let me put it this way, yeah. The essential notion here is the notion that I insisted yesterday, is the notion of universality. So once you have identified, once you're in a situation, so there is a broad range of there are families of short distance theory, short distance descriptions that end up giving you the same physics and long distance. Imagine you have different Lagrangians that are all different in the coefficient of dimension higher than, just ideally, higher than 4, of the term higher than 4, but they are identical here, then at low energy they do the same. Is this right? So the idea of lattice QCD is that the construction that you make, how the lattice is made, how big or small, if you change it by a factor of 2, if it is cubic or if it's another shape, the type of Lagrangian you write down, at the end of the day, it's changing all these guys. Okay? Because unavoidably, if the degrees of freedom that are light in this description are just the quarks in the gluon, at long distance, they can only be described by the only long distance Lagrangian for quarks in gluon, that is this one. So the crucial thing, however, you have to make sure that there are no other degrees of freedom. So when you construct this messy theory on this lattice, it's a piece of crap in general, okay? It's complicated. But in regions of measure non-zero in the coupling space, the light degrees of freedom, in other words, the excitations that have a wavelength longer, much longer than the lattice length, are those of the theory you care about, which is quarks and gluons. In general, you could have other degrees of freedom. Okay? For instance, in the field of quantum gravity, lattice gravity, it's not even clear to me that they have the right degrees of freedom. But if you have identified, if you're clever enough, you know that these are the long distance degrees of freedom, then you know that at distances much longer than the lattice length, where you can treat your system as a system on the continuum, because it's like for the multipole, you're no longer sensitive to the details of short distance physics, then the long distance dynamics will have to be the more general one, characterized by your degrees of freedom. And if you have been clever enough and your degrees of freedom are quarks or gluons, you're in the universality class of QCD. And this is what you have. I don't know what that is. Look, several different people, when you look at them from far away, they look the same. They look like a point.
Yeah.
You want to reproduce a point. Okay? The important thing is to have somebody there. Then if you have two guys, then it's 2 points. Just make sure that you have only 1 point. Then it's QCD. With the different points being the number of light degrees of freedom. I don't know whether. But the notion is exactly the same.
So I guess what would be my hang up is if you're saying we can ignore the short distance effects, then why aren't we just in the middle regime again?
No, it's not that we can ignore them.
So,
no, what I'm saying is not that we can ignore them. All this short distance effect will determine the value of this guy. They will be encapsulated in one single coupling.
Okay, so
that's the thing.
Yes.
And then that's the thing you measure, right? It's like when that guy is far away, there's only the details of that guy will be encapsulated by essentially 2 parameters here, the theta and phi, where the guy is. That's the angle of that. Okay. Everything else is gone. Whether the guy is nice or not nice, so it's just, and that's the same thing. All the story gets projected down to this.
Okay.
But that's always the case in physics. You are at short distance. All the details, as you go to long distance, all the details are encapsulated in fewer parameters. Okay. That's exactly like the multipoles. Exactly like the fluid, it's exactly the same. Only that in this case, what emerges at distances longer than the lattice length is just QCD. QCD of the continuum.
So with the multiple expansion, right? Being at lambda QCD would be like being at the distance.
Yeah, let me tell you perhaps in a different way. The theory, if you have a lattice QCD like this, and now you go distances, and now you ask yourself, what is the, let's say I'm doing experiments, I'm computing correlator at distances much longer than A, okay? And the lattice length. At those distances, do you agree that we expect to be able to describe physics in terms of a continuum? So then the question is, what type of continuum Lagrangian will we have in our language? Well, it will be a continuum Lagrangian of this type here, where the role of the cutoff, lambda, is now played by the lattice length. So the expansion, the derivative expansion that I had in the Lagrangian is now an expansion in inverse power of lambda, is an expansion in positive power of A. this is very much like in the multiple expansion, where the multiple expansion is the expansion power of A, and A is the size of the charge distribution, or in the case of fluid mechanics, where the higher derivative expansion is the expansion in the collision length. So there's always some microscopic length. And now, all the physics that has to do, all these other terms that you have that are proportional to A, have to do with the details of your lattice construction. Okay, but there are a few terms that are the leading ones, the one of lowest dimension, that are universal. And all your lattice construction for these terms just boils down in the specific value of GS. It's not clear.
Continue, please continue.
Is there any one of the so-called adults or senior or old guys who wants to give some help? No.
So what is the confusion?
The confusion is that apparently everything is very fuzzy.
Well, no. Okay, so I guess.
I like your insisting. I like your insisting. Go ahead.
Is I get why your statements are working in this middle regime, but to me, once you go down to energies at lambda QCD, right? Then like in the multiple expansion.
Right, at that energy, if you want to write. Okay, go ahead.
Like in the multiple expansion, when we bring R close to A, the expansion breaks down, right? Like
but this is like going in the okay. The expansion that breaks down in that perspective, the role of. Okay, let me say this way. This A that we introduce in lattice gauge theories is not physical. Do you agree with that?
Yes.
It's something we introduce. Okay.
Yeah.
Okay. And because space is not a lattice, okay? Gravity, that's not a lattice, okay? We introduce it, and we profit from the fact that precisely we're using this notion that the details of short distance physics, provided you have a separation of scales, do not matter. And we can turn that to our advantage computationally. It's only computational.
But I think this is because at lambda, if we're at lambda QCD, I don't see what the separation of scales is.
I think the confusion is that there's two different A's here, right? There's the bottom Lagrangian, which is the pi ineffective Lagrangian, where the A is 1 over lambda QCD. And you're right, if you tried to use that at lambda QCD, it would fail.
Exactly. If you are a low energy, if you are a physicist in a very poor planet, where you have not been able to build an accelerator at energies above 1 GeV, you live here, then for you, the ultimate scale of your physics is this 1 GeV, and this is what you would call the analog of the size of your charge distribution. As long as you do scattering with pions with very long wavelength, you only see the low energy tail of all this stuff, which is like being very far away from then when you go to high energy, then it's like getting close to the charge distribution, and then things get more complicated in your description, okay? In your description in terms of pions, and you start getting more and more terms, okay? And when you get here, the expansion breaks down, and which is like when you are in the middle of this charge distribution, and you essentially have infinite information. But now, when you get in the middle of the charge distribution, it could happen that you discover that it's just something like that. It's something, again, very simple that you can describe in a different way in terms of a few parameters. In fact, what happens here, now on Earth, we are rich enough to have gone up and discover that when you go to yet shorter distances,
so
the physics becomes, again, describable.
Say if I'm in the middle region and I go down, right, to like I approach lambda QCD from the top, this expansion doesn't break down.
This expansion doesn't break down. What happens?
Okay.
What happens? What happens is like here. There is some coupling, okay, that becomes strong, okay, And perturbation theory breaks down, but breaks down in the infrared. It breaks down in the infrared.
So the expansion, like the Lagrangian description, doesn't break down. It's
No, it does.
perturbation theory.
It's the perturbation theory. Oh, sorry.
Yeah, yes, I think this was, yeah, okay.
Yes, but again, it's always the problem of reductionism. Look, it's always this. Problems in the UV are unsolvable. Problems in the IR is simply that you cannot do the computation because all the see, when you go towards the IR, we have all the information. It's just we are done. Okay, we are not strong enough to do the computation. In the UV, we're really missing. It's really the ontology that we are missing. We don't know what we are dealing with. In the IR, we are just weak. Is that the thing?
Yeah, no, I understand now.
The only way to go across this, because there is all this information, is to have some principles, okay? You need some principle that allows you to travel this infinite space of parameters. This is why I think, for instance, that this thing like asymptotic safety is garbage. But that's my opinion. Because you just hope to go across the wall of fire without making any assumption, just by computing. Okay, so I already eaten up my lecture. Okay, good.
Sorry, this is not a greatly formulated question, but when we talk about scale invariance that occurs in the middle regime, it reminds me of a situation in StatMech where at phase transitions, a lot of the coordinate quantities have scaling properties and correlation lengths diverge.
Sure, that's the same thing. It's again here, okay, take here. In StatMech, they're very good lab technicians, very good, okay, they pay their money. And these lab technicians are there only to set all these couplings that grow with energy small. They set them to 0. When they're 0, the scale where the transition goes to 0, the correlation goes to infinity. And that's the language. Is that okay? Yeah. But they're lab technicians, we don't. Is that okay? Okay. So I think I screwed up completely now, but that's okay. I think it's more fun like this. It's better to do little and not have misunderstanding than just give you one and then. The thing I want to say is that it's going back here. I want to say something about this notion of scale invariance because it's very, very, very important, and I think it's a perspective that any particle theorist should have clear in mind. Okay, and I want to say something about that. Okay, so as I said, in all the examples which I presented here, which either we know because of experiment here and here, or that we have speculated about because of work by us, okay, theory of unidentified theories. In the presence of this separation of scales, as I said, there is this desert and the system behaves like approximate scale invariant, but it's a specific type of scale invariant theory. All these theories are theories that are approximately free, okay? In the regime between, say, the W mass and adequacy G strong is not so strong. In first approximation, you can neglect. In fact, this is why we say that here is a theory of quarks and gluons. Why we can say that? Because quarks and gluons are weakly coupled. Okay, so if they were strongly coupled, we couldn't even separate one from the other. So the fact that we can say that here we are quark and gluon is because we are quark and gluon and they are weakly coupled. So in first approximation, the Lagrangian, you can even neglect GS, and the first approximation, the Lagrangian is a free Lagrangian, and a free Lagrangian without mass, a massless free Lagrangian is scale invariant. Now, it turns out that the leading coupling is this, which is also classically scale invariant, and its non-scale invariance is purely due to quantum effects, and it's slow, and it's in fact the reason why ultimately this description breaks down, but not that it breaks down in the sense that we don't know what the theory is, in the sense that we cannot compute. Okay, sorry, I really confused you completely with this picture, but you're complete. I will learn for the next time I give my lectures. Now I will. you are completely right. Okay, but you see, but saying that, and the more the larger the separation of scales, the better in a sense the scale invariance. Okay, because if you want to have the scale very separated, then GS has to be smaller, otherwise it runs strong, and then you get again a new scale here. Similarly, if the scale goes up, then all these higher dimensional operators become small. So essentially, the larger the hierarchy, the better and the longer the theory is approximated by scale invariant theory. Which is just to tell you that the notion of scale invariance is essential in understanding large separation of scales. And as I said, large separation of scales are, in a sense, the reason why we can do physics with few parameters, or if you want really to be even stronger, why we can do physics at all, in a sense, okay? So, because of this set of, if you want, syllogism, or if you want, of connections, understanding scale invariant is very, very important. Now, there is one and because it could be that, why not, in the next stage of physics, when we go and look above the standard model, we will have a scale invariant theory, but it may be a different type of scale invariant theory than the one we are dealing here. It may not be weakly coupled. Okay? And in condensed matter, the example of scale invariant theories that are strongly coupled is ubiquitous. Okay? So it makes sense to understand strongly coupled scale invariant theory because it could be what hides behind here, in principle. Okay? Or, yeah. Now, it turns out that there is something, so understanding scale invariant theory is the first part. Now, it turns out that there's a very interesting fact about scale invariance in relativistic system, in relativistic field theory, is that scale invariance implies a bigger symmetry when put together with the Poincare group, and the bigger symmetry is the conformal symmetry. So this is why this scale invariant theory are normally called conformal field theories. Okay, and I want to say very few words about it in a non-technical way. So let me tell you something about space-time symmetries. Okay. And scale invariance. Okay, so you're familiar with the Poincare group, okay? The currents that are associated with the Poincare invariance through Noether theorem are associated with the energy momentum tensor. The energy momentum tensor is the encapsulate the set of currents associated with that. And how does it work? Well, Poincare group, what it consists of translations, okay? And the invariance and the translation gives you 4 conservation laws corresponding to 4 currents. The charge is the 4 momentum, and the object is nu, okay? Okay, so these are the 4 constants. Nu is a 2-index, it's a 4x4, it's a 2-index tensor, general 2-index tensor, okay, at this stage. But if you have also invariance, which you do have in Poincare under Lorentz transformations at the infinitesimal level, omega mu nu is just an antisymmetric set of generators of the Lorentz group is the set of antisymmetric 4x4 matrices. And so this imposes other conservation laws which appear in the form of constraints on T mu nu. And T mu nu, you can raise the indices by using the Lorentz metric. It's also a 2-index tensor, very large, like this. But so what is omega mu nu? Omega mu nu is 6 objects. It's an antisymmetric Lorentz tensor. Actually, from the point of view of the representations of the Lorentz group, which is SU2, the algebra is equivalent to SU2 cross SU2, okay, plus minus. It's 1,0 plus 0,1, okay, from the point of view of the, so it's 6 6 objects, okay, 6 quantities, and 6 real quantities if you want. And expectedly, this should give you 6 constraints on mu nu, and this constraint should be in a sense covariant. So what does it do? Well, it kills the antisymmetric parts of mu nu. Okay. Lorentz invariance implies that mu nu is symmetric. Okay. And the corresponding current, okay, is written like this. Sorry. Okay. Okay. And that's it. So it's what it is. Okay. Now it turns out that in the theories we're interested in, there is another approximate symmetry, and that's dilatations, where delta mu changes this way. Okay, just get dilated. Again, see, the point is that the energy tensor is the generator of translations. Okay, this is like, well, this is an ordinary translation, this is a local translation, this is yet another local translation. So what is the parameter of this other local translation? Well, it's lambda. You compute this lambda as you compute this as lambda eta, or this is the Lorentz metric, x nu, okay? It's the Lorentz metric, so lambda is a scalar, okay? So lambda is 0,0. So this will give you yet another constraint on mu nu, and by covariance, what can this constraint be? Well, this will involve the only remaining, must involve a 0,0, say a Lorentz scalar in mu nu. So this is the trace. And what you have in this case is that the trace is 0. Now, this is a bit fast and loose, okay? There is another option for that, that this trace is equal to the divergence of a current. Turns out that that possibility, and we still don't completely understand it, I think, is never realized in the interesting cases. Okay, so as a matter of fact, all scale invariant theories that matter have this property. Okay, so the trace is 0. You can understand. You're very familiar with this fact that when you have, for instance, a gas of relativistic massless particles, which is the primeval example of a scale invariant system, the energy momentum tensor, mu nu, which you can write as rho 0, 0, and p in the diagonal, satisfy precisely this condition, right? That the pressure is a third of the charge density, okay? And the trace is 0. Okay, that's the standard thing when we do cosmology. Okay, but that's a consequence of scale invariance. Now, it turns out that in a situation where the trace of t is 0, you can write another conserved current. Okay, you can write another conserved current, which you can write as k mu nu, or in the following way, x okay, let me just do it like this. X mu x rho t rho nu minus x square t nu, something like this. Did I screw it up? Maybe I screw it up. Okay. No, it's I screwed it up. Sorry. X nu. So yeah. Sorry, I'm a real idiot. This one should not be changed. exactly, this was not, yeah, this is correct, okay? So there is this other current, and you can check that this current is conserved. If T mu is 0, and this current is just you can view it as the energy momentum tensor contracted with some specific coordinate transformation, okay? It's like, this is like some delta x nu x rho, t nu rho. This is transformation of the coordinates, so delta x rho is 2x nu x rho minus delta rho nu x square, okay? So this is the infinitesimal transformation of the coordinate which is induced by that. And now it turns out that theories that are endowed with this additional symmetries is special conformal. In a sense, it's like, it corresponds to 4 conserved charges like translations, okay? And these generators, I mean, there is, I mean, I don't want to get into the details, but the presence of this symmetry makes the theory very, very special and very, very constrained, okay? So that is to tell you that on general grounds, when there is a separation of scales, the class of theory that describe physics in the between, if the separation of scale is very large, in relativistic invariant theories, is very, very constrained. And in the normal case that you're seeing here is approximately free theory, which is a very constrained system, okay? But this, in general, okay, this is really consisting of these conformal theories, okay? And conformal theories are, of which nearly free theories are a special case, are important for these reasons, and they have very, very special features, okay? We should think of them in a different way than what we're used to think in terms of perturbative theory where we write the fields. The basic objects that define these theories are the operator spectrum.
Sorry, excuse me.
Yes.
The camera's only pointed at the main board, so could you either zoom out or turn it? I don't know if that's possible. There we go. Excellent. Thank you.
Okay, sorry. Yes. So the theory is characterized by its operator spectrum. So tell you which operators you have in the theory, which of course for a free theory, you know very much which operators you have. You take the fields, you multiply them, you put derivative, these are the operators of your theory, okay? And well, here it's abstract, okay? There are some operators in this theory, and they're characterized, these operators, by their scaling dimension, okay? This operator O alpha, and this alpha is an index, okay, local operators, which is controlled by essentially the spin of the operator or its transformation property under Lorentz, the dimension, the scaling dimension, and you know very much what is the dimension of an operator. Here in free field theory, you know how to count it very well. This is 4. This is 4. Okay, you count 3/2, 1. Okay, and the peculiarity is that the dimension of this operator, when the theory is strongly coupled, can be non-integers, while all the weakly coupled theories have the property that their spectrum of operators, at least bosonic operators, is integer, and for fermionic is half integer, okay? In general, the set of dimensions will be whatever, okay? It will be non-integer, which meaning that when you perturb the theory, the higher order terms, let's say the irrelevant operators, can in principle, will scale with arbitrary powers of non-integer powers of the high scale, okay? And the dimension in terms of the operator is simply it tells you how its correlator works, okay, depends, this was like 1 over x squared to the delta, okay? This is just the dimension is fixed by the two-point function, okay? So spin and dimension, so maybe chart if there are some other concerned quantum numbers, isospin, and so on and so forth. So these are, so which operator you have for with what spin, with dimension, with chart is one part of the information that defines the CFT. And what is remarkable is the rest of the information is completely fixed by the 3-point functions of any 3 operators, okay? So these are what called you call the alpha 1, alpha 2, alpha 3, okay? And in fact, the coordinate dependence up is essentially fixed, okay? Given these operators, given their quantum numbers, okay, here, the coordinate dependence is fixed up to a finite number of numerical coefficients. So this set of numerical coefficients for all the triplet of operators and the spectrum completely define the theory. And it's a very mathematically, if you want, well-defined set of data. This is called the CFT data, and using this fact, okay, and other properties of these theories, we have started. I mean, the community has started exploring in a more quantitative way this class of theories in the last decades. Okay, and in a sense, you can think of this, the possibility of this theory being relevant. In a sense, these theories constitute a reservoir of possibilities. It's like a dark sector of theoretical possibilities that are hard to investigate using perturbative method. In other words, the perturbative theory we have, besides the fact of being relevant for physics, are those that we can really work out with on a piece of paper. The general conformal theories, some of them may not even be writable in terms of a Lagrange. So the existence of these possibilities suggests that it may well be that the theory that describes physics about the weak scale is one of these abstract theories which we cannot really write in a Lagrangian way. And all we know is that this theory is there because for some reason there's some big separation of scales. Okay? But that's all I wanted to say about it. I think I can take a little break, probably. So I get a moment to stop and then I'll start.
So we start at 11:45?
Yeah, 11:45. 11:45. I think I'm a bit behind.
Talking right before. For today, we right after.
No, but like, like, just gonna always use it. Like, right. No, well, they ripped organically, right? Like, this is where. I know, I don't like, I try to.
I saw that.
But they just keep ripping. No, they were like a little gray, and I put them on, and my toe went right through the brake part and ripped it. I was so sad, and I was showing my brother just yesterday, I ripped it again. My life, right? They're ripping everywhere.
Because there's the graduation.
Oh, right, yeah.
Però sicuramente l'esempio accademico invece
Oh, yeah. So,
Yeah, it's definitely gonna have to go back.
yeah, I think the thing about this is
I mean, I don't know.
These are fields that like I guess they would, like when you define the class period, they would act on some state.
però poi dopo
The scale of the old
non è che c'è
Sì, sì, cioè penso che credi sia questo. Uno si calcola, teoricamente dovrebbe calcolarsi.
Like, for example, when we take expectation values these like correlation functions called
questo
plastic
boundary value
they
non
are
funziona
boundaries.
in libertà, però solo dopo aver fatto l'integrale no, potrebbe pensare.
So I think what he's saying here is that in one theory they're described as extra
Sì, esatto, questo è il così
and it turns out that the symmetry is so good that the two-pointed functions for
l'unico problema
without even doing it. So the symmetry comes from so you know the two-point function you know that
O anche se non è preso per quale prezzo devo vendere.
you could say actually the three functions goes like x minus y
questo logaritmo che c'è qua adesso è il logaritmo
you don't need to know
quindi non ci sono
Però come dicevi tu, se penso a omega k,
yeah that's a bit
è doppiamente una cosa, se adesso a un certo punto voglio considerare che è doppiamente una cosa monolitica, ma capisco un attimo.
no, sono d'accordo.
Infatti mi sembra proprio che il logaritmo sia questo, cioè sembra prendo il logaritmo è definito poi ed compare sempre
Oh, like the radius of stuff.
Right.
però stavo un po' dentro questa cosa ed è una statistica
yeah so for example back to you set up your branches so all your indices are contracted because you want to so here you set it up not only do you have variance but you also have like if they stay
Sorry, like stop it. Okay. I don't like it, but
Oh, yeah, definitely. Oh, maybe.
yeah so you see that in but like if you step right I see like the only way I can see videos are videos like we see the transition like fluid to gas transition
right.
can't like whether you zoom in or out like there's to me that looks like scale that seems different. That might be different. Here we're not talking
That's really interesting.
Yeah.
yeah. It's not like that there's some
Project is becoming very complicated. And if you're coming at it from the other side, I know the theory at higher energy. Going down to it, it's simple logic, it's fun. That was the conclusion, right?
something where
Computational challenges, that first goes on. I think that's what.
Yeah.
Yeah, sure.
you mentioned it just now.
Let's stop
about that.
I don't know.
What? How were your parents yesterday? By the way around. Like, they know the address, they're good.
It's a discrete method of computing things. That's all I got.
Yeah, I know, sorry. And have afterwards. I guess that's what you do. Tanya lives right now, so I'm gonna go.
Oh, right, and who's the person
That's
saying
it, yes.
Yes.
Yeah, when he was saying generally, you can depend computing, and in practice that shooting is. Yeah, it'd be nice to have a crash course in like a very intro. No, like not for anyone trying to do it, but just like so to have an appreciation of what's going on.
Not to teach you how to like calculate things.
Right.
Oh, yeah?
I feel like a lot of things.
Yes, I mean, yeah, this is the challenge. When a course on a topic is too much, and I don't know what like a one-off seminar is like.
Yeah.
Where
Oh, I see, that's big shot.
yeah, it's like challenge. Yes. But like, it's like as the guy knows that that could be an interesting just make a list of these topics, find some papers and like just
Right, so we just did like Andrew's game.
There's a way to make
they were doing a focus on generalized symmetries and
So let me start. I will now get into the second part of my lectures with, of course, some delay, but that's okay. I think I'd rather do little than do a lot and go fast. So this is the subject of symmetries. And naturalness. So there are two classes of symmetries that are relevant in physics, in particular in particle physics. First is gauge symmetries, and the second is global symmetry. Gauge symmetries, as nicely explained in Weinberg and also in his books, they just arise as from the need of coupling in a local Lorentz invariant way massless fields with spin 1 or higher. So they are essentially redundancy in the description of the system. They are, in fact, inclusively the color symmetry is not even visible. Okay, so I will not discuss that. The symmetries I will be concerned with are the global symmetries. Okay, and why are these symmetries relevant to the discussion we were having? They're relevant for the following reason. When you have the picture we'll be looking at, okay, where for some reason there is a big separation of scales, okay, in all the cases we have considered, okay, all the cases we have considered so far, starting from the multiple expansion onward, okay, we have a situation where no matter how complex the original system is, at long distances or at low energy in quantum field theory, the number of relevant of parameters that really matter gets reduced to just a few. Okay? And when that happens, it's understandable that accidents may happen. Okay? The very fact that you have very few parameters puts in a very constrained situation where they can arise what we call accidental symmetries. Okay? So accidental symmetries are one feature of this, if you want, simplification that arises in the features of the system when you go from high energy to low energy. If you can do that, okay, if there is a separation of scale. If there is a separation of scale, things at lower energy looks much simpler than at high energy, simply because you see concretely when you go to low energy, all this tower of operators, which is virtually infinite, becomes irrelevant, okay, you don't see it, and then you have only few parameters. So in that situation, symmetries can occur, symmetries which may be then broken by the full tower, but symmetries of what remains, and in that sense they are approximate. But they're approximate, or even better, the term is accidental. Okay? Accidental meaning that they only arise because we've done this separation of scales. Let me explain with a little cartoon how this works. Okay, so imagine you have a guy. Okay, as I was saying before. Okay, here you have a guy. Here, he's smiling. You get closer. Well, you actually discover this guy. A little devil. Okay, you get closer. Okay. And it has a lot of features. So in particular, if you rotate it, it looks different, okay? It's not invariant under rotations. However, if you go very, very far, okay, this thing will look like a point, okay? So while here, when you are very close, this, you can say that SO3 is broken, or well, if you are here, it's SO2, okay, more on the blackboard, okay? Here, you have SO3. From whatever direction you look at this guy, if you're far away, it looks the same, okay? It looks like a point, okay? So you have gained a symmetry, okay? And again, the symmetry is only arising because you have a separation of scales. And in fact, you can quantify this, you can make this less cartoonish by going back again to the multiple expansion, okay, that we had, remember, distribution of charge of size A, this is rho, and the resulting potential consists at long distances of the monopole plus the dipole plus the quadrupole and so on and so forth, okay? So how do you see, so in general, this distribution of charge will be like a potato. You can think of this as like a potato, okay? It does not have any symmetric feature. However, if you are at a distance such that with your precision, the only thing you need concern with is the monopole, in practice, all you know about this distribution of charge is that it's spherically symmetric. Okay, so here you have, if you are sufficiently far away that you only measure the monopole, you have gained, well, you have gained, it's just because you're ignorant, okay? You have gained a symmetry, okay? Now, if you move a little closer, and you maybe can measure the dipole, you no longer have that symmetry, but you still have a subgroup. You still have SO2, okay? You have the cylindrical symmetry. If you go even further, and then in general, you may have some discrete symmetry in some cases, but you have no symmetry. Okay? So you really see that when going to fx, this is a to the 0, this is fx of order a to the single power, this is fx to the order a squared, you get precisely. So when you go, so the knowing more and more about this, the structure of the system generically reduces the symmetry. Okay? So again, so in that sense, symmetries in this respect are connected again to this existence of separation of scales. So, and this silly cartoon actually contains all the relevant information. But let me give you at least one example of a symmetry like this, which emerges just from the fact that we are sufficiently far, in other words, that there's sufficiently scarce separation that we can truncate to the very first terms, is called an accidental symmetry. Okay. Now, accidental symmetries are ubiquitous in physics, and they are particularly important in particle physics. Yet another example of accidental symmetry is parity, okay, in QED. So parity was for many years considered deep symmetry like that, and okay, well, the reason why parity is so important is because when you go to low energy, it's very hard to break it. And if you take, in other words, you don't have enough term to break it. If you take QED, let's forget for a moment other interaction, just focus the interaction of a photon with an electron. Again, if you write, again, QED, like all other theories, will have to be a theory with a very, very, very long tower of operators. But if you are sufficiently low energy, in a situation where there is separation of scales, we will only see the first few, and the first few are the gauge kinetic term, the electron kinetic term. There's the electron mass. In principle, you could add some other term like delta M with a gamma 5. You can also add some coefficient f mu tilde, and then everything else is suppressed by some scale, okay? The higher dimension operators. We can in reality we know what this is, but let's think of QED as an abstract theory, which is the theory of interaction of a photon and an electron field, okay? And all that there is this. Now it turns out that if you look at this Lagrangian naively, you could think, oh look, this is parity odd. But in reality, you can always make a filter definition, okay? You do a summary definition like this, some beta gamma phi psi, and you can absorb this into the mass, okay? And then this you can eliminate. In other words, you can define parity in such a way that this Lagrangian is invariant, even though naively it looks like there is a gamma phi. This object here is a total derivative, and in this particular weakly coupled theory, it doesn't give any effect, so it integrates to 0 when you compute the action. And so the action is reduced to this, okay? And this, in the case of QED, as concerns parity, is the equivalent of that, okay? Is the leading order term you can write down, and it turns out to have, just as a consequence of Lorentz invariance, locality, and the fields you have, there's no way to write a parity breaking interaction. So parity is unavoidable, okay, at this level. Then the question is nature making an effort to make parity a symmetry? Well, no, because as you know, in physics, you add the extra term here. There are extra terms that come from short distance physics. Particularly, there is the effect of the exchange of the Z boson. Okay, this is the electron. And this gives you a term that goes like psi bar gamma mu psi bar gamma mu gamma phi psi divided by the mass of the Z times the coupling. Okay, so this is a dimension 6 operator. It's the very first. This is the very first chance to violate parity when you do this expansion abstractly. Okay, if you were to consider abstract QED, in fact, you could even have it already at dimension 5 with an ED electric dipole moment. But okay, in fact, this is one of the few instances where you can have it. Okay, here you cannot break parity, and in fact, in reality, you do have that. So just to show you that parity, nature doesn't seem to care so much about parity. Okay, it's broken by the standard model, but still in QED, okay, given that the relevant scale of QED is 0.5 MeV, okay, or the very low range where you discuss the electron and photon interaction is much smaller than the mass of the Z. You can neglect these effects and have a situation where parity is a good symmetry. In fact, parity is therefore also a very good symmetry of atomic physics, and it takes quite some work to see the effects of parity breaking in atomic levels. In other words, operators like this, in particular also operators that involve protons, break parity, give rise to mixing among atomic level of different parities.
So when you're talking about scale here, then you're talking about energy now, or are you still talking about length scale?
Okay, since when I'm in field theory, since we are doing relativistic quantum mechanical theories, talking about length scales and mass scales is the same thing. Okay? So when they say high energy, I mean short distance, it's interchangeable. When they do classical physics here, well, that's a different thing. Okay? Yeah. Okay. So yes, maybe sometimes I say one thing and I mean another. I hope this doesn't cause too much confusion. Any other question? Okay. And we will see later how the notion of accidental symmetry is, I think, it emerges as offers a critical way of looking at the standard model. Okay, this is why I'm presenting it here. Okay, but that's the essence. So this is the first things I have to say about symmetries. The next thing I want to say about symmetries is I want to recall the notion of selection rules and dimensional analysis. In fact, selection dimensional analysis are just a specific example of selection rules. Okay, so symmetries are normally emphasized as beautiful, as nice when they're exact. Oh, there's a symmetry, there's another theorem. Oh, this is so beautiful. They're actually equally important when they're not exact, even when they are badly broken in some cases, because, and this for, if you want, technical reasons, it's because you can always treat the parameters that break symmetry that, okay, but I'm not even saying, I say it in words, okay, otherwise it's taking too long. You can always use the parameters that break the symmetry, you can always assign them formally transformation properties under the symmetry that they break, okay? And this trick, it's just a technical trick, allows you to track how these parameters affect physical quantities, okay? This is the essence, if you want, of dimensional analysis and selection rules, okay? Let me recall, and they're an important concept for formulating the notion of naturalness, okay, which I will do later on, okay? So let me give you, again, examples. So I'm talking about dimensional analysis. And selection rules. And I just want to emphasize that they are the same thing, okay? You've heard about selection rules when you've done maybe quantum mechanics or atomic physics. I will recall, in a sense, the notion. But it's the essence, is using symmetries to track how parameters appear in physical quantities. So let me start with dimensional analysis. Let me recall, really, I'm not afraid here of saying trivial things, okay? What I'm saying here is absolutely trivial, but be warned, okay? So you're familiar from mechanics of the use of dimensional analysis, okay? What does it mean, dimensional analysis? How does it arise? Well, it arises, let's say, in the following way. You can think of rescaling your variables, let's say your spatial coordinates, by some lambda x, lambda space x, collectively, okay, all your particles, position, maybe, okay, and times, okay, lambda time prime t. Okay, this is like changing. Okay, so what is a symmetry? A symmetry is a change of point of view. Okay, you rotate something. You can either view it as rotating that something, or you can view it as changing your reference frame. And here you can see it as going from, say, France to England and changing the units from the metric one to the absolutely incomprehensible imperial system, which is also used in the US.
How the UK converted? How the UK converted to international systems?
After
More
Brexit.
or less.
After Brexit.
Well, no, more or less. It's not true.
That's even worse. They're in the transition. They're in a quantum
The
state.
speed is mile per hour on the motorways.
Anyway, so you're familiar with the Lagrangian. So how does the mesh analysis work formally? Okay, your Lagrangian will be a function of x of t, x prime, x of t prime, x dot of t prime, and some parameters. Oh, shit, we call this parameter gi. Okay, some couplings, okay, and so normally if you go to the new description, okay, if you use the new variables, what you will have in general, if you have a symmetry, okay, if you have symmetry, if you have symmetry invariance under the scaling of x and t, you will have that this is x prime, you will have the same Lagrangian, x prime of t prime with the same coupling, okay. And in fact, since we are doing classical physics, we are only concerned with the stationary points of the Lagrangian. So in general, the notion of invariance as a slightly more general implementation, you have invariance as long as the Lagrangian changes up to some constant coefficient that depends on the transformation parameter. Normally you're familiar that the symmetry is the transformation that leaves the Lagrangian invariant, but that's true in quantum mechanics because in your path integral you're e to the I, the action. In classical physics, you're only concerned with the stationary points of the action. So if the action can multiply it by a factor of 2, the equations of motion remain the same. And that's all that we have in classical physics, the equations of motion. So anyway, beside that.
Sorry, but even without this subtlety, one should really look at the action, no? Because if you're rescaling time.
Yeah, but I agree with you, but I don't need rescaling space because I'm not integrating over x. So there could be rescaling from lambda x. Okay? Yeah, I agree with you, yes. But if this is the action, that appears in the already. I already. Okay. Yeah, you're right. Yes. Anyway, the action can multiply by a constant. You're right. Okay.
And by total time derivative. And by total time derivative.
Anyway, in this case, this is not. Yeah, if you do Poincaré, if you do Galilei, it's okay. It's okay. Let's not get into this. I'm doing something really trivial here. So what's the deal here is that however, in general, this is not a symmetry, and so what will happen is that this will be true, but here with some other G prime, which are precisely the transformation. We define a set of formal transformation of your couplings. If you want, you can treat your couplings as dynamical variables, and you transform them suitably. The G prime is equal some powers, lambda t and lambda s, some other power, which characterizes the dimensionality of these objects. Okay, if you want, this is the story, and then you have in that respect, you have this relation. Okay, and this tells you simply that any dynamical statement done with this choice of variables translates into an equivalent statement made with these other variables, okay? And the way that works is that, let's say, you have the equations of motion in these variables, you transform the variables, and you get the equation of motion in the other variables, okay? And when you have quantities, you have some dynamical relations in these variables. If you transform it, this you will get the same. If this object here transforms in a definite way under this rescaling, this will transform in the same. So in other words, dynamical relations are covariant under this change of parameterization. And this, if you want, and now, in order for this to be covariant, if A transforms in a certain way, B must transform in the same way. And this fact gives you a constraint on the structure of these relations. So if you take, for instance, the pendulum, okay, just the simplest possible dynamical system, okay, you take the pendulum. Here you have three parameters. You have L, the length, you have the mass, and you have the acceleration of gravity, okay? And this object transform under, if you apply the same gain to the pendulum, you have that L prime is lambda x L, G prime is lambda x over lambda t squared G, and M prime is equal to M, okay? And now if you have the main dynamical relation here, which is the frequency for small oscillations, for larger oscillation also the original velocity matters because they're not harmonic. But if you take the frequency for small oscillations, this should be a function of the relevant quantities L, G, and M, okay? And well, in principle, you can also rescale M, okay? You can also add another, let's take M out of the game, okay? Because then it will disappear, okay? And the only way, and this relation should be covariant under this transformation, and the only way that can happen is that omega depends on your quantities, precisely this way, okay? So this is just a consequence, if you want, of a symmetry, okay? Of a symmetry that is not a symmetry, but it's like a symmetry that is broken explicitly by your parameters. You can always view this parameter as things that transform under the symmetry, and that restores your. But you see that the transformation property of G and L under this transformation fixes completely the way the frequency of oscillation depends on them, up to a numerical coefficient. Of course, this doesn't tell you whether this numerical coefficient is 1 or 10 to the minus 20. It could be 10 to the minus 20. If you get 10 to the minus 20, well, I think this is suggesting that you need some more investigation. There's something very interesting going on that that you're not getting. So this is the way, and so dimensional analysis is just the implementation of the explicitly broken dilatation symmetry. In classical mechanics, you can make independent dilatation for space and time. In quantum field theory, in relativistic quantum field theory, we treat space and time as the same thing, and there's only one dilatation we do, okay, which is the dilatation of the coordinates. And applying the select, sorry, this the statement that the fact that the left and the right hand side of this equation are shown in the same way is what we call normally physics a selection rule. Okay, so we have different we have a physical quantity with some parameters, and there is a symmetry under which they all transform, and by covariance under this symmetry, the transformation should be the same on both sides, and we call this selection rule. In other words, dimensional analysis fixes the powers of G and L that appear in this formula. G appears with the 1/2, L appears with the -1/2. Okay? If you want, these are the dilatation charges of these corresponding objects. Okay? Quantities. Okay? Good. Okay, so this is just good all-dimensional analysis. Now it turns out that this is in no way different than the ordinary selection rules that you're familiar from, for instance, atomic physics. Let me give you an example of that. So in atomic physics, what is the relevant thing? The relevant thing there are rotations, SO3, and maybe parity, because I just said that these are relevant symmetries. Now, example, the question that you can ask yourself. Imagine you take an atom, okay, in its ground state. I don't know how to say it this way. There's an atom in its ground state, and you slowly turn on, and the ground state is spherically symmetric, it's a state of zero angular momentum, and you slowly turn on an electrical field, okay, so that the system will be in the resulting ground state, at the end will be in the ground state with this external electrical field. So the electrical field will change, will affect the way electrons and protons move inside, and generically you expect to generate a dipole, okay, an electrical dipole, okay. So the question is, so as you turn on the electrical field, the original ground state of your atom will be mapped into ground state, which is a function of E, which in general is not, which will in general not be a rotational invariant state, because you are in a presence, you're in the background where rotational invariance is broken. So here, E, you should view E, even though E is a field, in this example here, E is like an external parameter that breaks the symmetry, in this case rotations, very much like here, or actually the pendulum, which I just erased, the length of the pendulum is an external parameter that breaks dilatation invariance, and the acceleration of gravity is an external parameter that breaks a combination of space dilatation and time dilatation. And so it's an external parameter, and then you can ask yourself what, and in particular, what you have is something that you can check for yourself, is that if I rotate E, okay, if I were to consider another experiment where I have rotated E, okay, the rotated state they end up with is the quantum rotation, the representation of that rotation on the Hilbert space acting on this state. Okay, it's just rotating E is like acting with the rotation operator on the state. Okay, and this actually now with this you can ask. So what can we say about the expectation value of the dilatation of the dipole operator in this state, okay, what can we say? What can we say, guys, about this? Well, how do you expect this to depend on E?
Just the magnitude.
Eh?
Just the magnitude. Like the rotation, like when you rotate E, it should change.
Okay, so the statement, as he's saying, is that this object, if I now act with the rotation, if I rotate this, if I rotate E, it's like acting with this rotation operator on the, I'm being very formal here, even though I'm saying something trivial, on the rotation operator on the state, and acting on the rotation operator on the state is equivalent to rotating D. Okay? So rotating E is like rotating D, so what you have here, the other side should transform in the same way, so it should be something proportional to the electric field itself, times a function that only depends on E squared, something like that. So this is just the result of SO3, right? And this is exactly the same. Of course, it doesn't tell you precisely what this function is. You cannot know this function. You don't know the normalization. When E goes to 0, this in general will be some number, okay? Doesn't tell you how big it is, but it tells you that it is aligned, okay? And then you may say, oh shit, I already knew that that is the case, right? If I turn on an electric field, then of course the thing stretches in that direction, right? But actually, if you go to 2 dimensions, but you see, if you look at this, this is essentially the fact that here there is, yeah, okay, that there is, if you write it formally, you can write it this way, okay? It's like, in general, there will be a matrix here, okay? At first order, there's some matrix f of E. Let's go to very small e, we take the linear term, it's going to be something like this, but in order for this object here to transform in exactly the same way as this matrix should be the identity. Because the identity, ij, is the only 2-index tensor that is invariant under rotation we have in 3 dimensions. Which tells you automatically, when I say 3 dimensions, this is the only 2-index tensor invariant that we have in 3 dimensions, tells you immediately in 2 dimensions things are slightly different. Because in 3 dimensions, there are 2 dimensions there are 2 invariant tensors. One is delta ij and the other is epsilon ij, which have different transformation properties under parity. And this is odd and this is even. And this tells you that in 2 dimensions, if you were to do the same thing in 2 + 1 QED for a 2-dimensional atom, if for some reason parity is broken, then here you can have, this is in 3D, but in 2D, the same thing can have 2 functions. One is EI F1 of E squared, and the other is epsilon ij, ej, some other function of E squared. Okay? And this, again, these are all, this is why, well, because this is an invariant tensor and this transforms precisely the same way under 2-dimensional rotations. Again, these are examples of what we call selection rules, okay? But as you see, they are exactly the same as what we have here. They simply follow from the notion that you can assign, if you're clever or if you're not so clever, okay, transformation property to parameters to figure out aspects, okay, maybe not all of it, of their appearance in physical quantities. Any question on this? Okay. And this goes on. It goes on. For instance, take for instance the standard model. Okay. Take.
So tell the ground state was unique, not the general.
By the way, in 2 dimensions, this situation where you break parity can be obtained when you turn on a magnetic field. Okay, 2-dimensional magnetic field corresponds to having this J. It points in the 3rd direction. So, okay, another example, okay, of and of course this broken symmetry, the impact of broken symmetry is very useful in understanding how things depend on parameters. Let me give you another example. In the standard model, you have the interaction, W interactions, W boson interaction. okay? I always give a classical example, standard quantum mechanical, and then field theory. The emphasis is just there. It's always the same thing, okay? So here, what do you have? Here you have W mu, the W boson, couples, there is a coupling here, G weak, with the let's say the up-type quarks, left-handed quarks of flavor I, and there is a gamma mu, there's 1 minus gamma 5, it's a left-handed current, D left J, okay, and in general we know experimental that this vertex exists for all type of flavors, okay, and the coefficient that controls it is the Kobayashi-Maskara matrix, okay, CKM matrix, okay, that controls the Lassard-Mission conjugate, okay, Lassard-Mission conjugate. Now, so there is a symmetry you can think of when you have different families of Fermi. These are the flavor symmetries. It's a symmetry which counts at the end, whose charge would count how many quarks of the given type you have in a certain situation. So they are just the phase rotation of the corresponding quark fields. And the I goes to the e to the I, theta I of dl, and UL goes to e to the I, theta UI, ULI, okay? These are just phase rotation where for each flavor, whether up and down, you can have a different phase. So this is a set of 6 U1s, one for each of the 3 up and 3 down type quarks of the standard model. Now, this would be a symmetry if you only had the kinetic term of the quarks, okay? The kinetic term of the quarks is invariant under this, but this interaction is not invariant, okay? It's not invariant because this matrix mixes different families. On the other hand, if you formally assign transformation properties to this matrix such that Vij transforms in a compensating way, this is a formal thing, okay? So Vij transforms like e to the I theta Iu minus theta dj, Vij, then this would be the same. And so this fact, okay, very much like the rotation properties of the electric field here, or the transformation properties of the length and the acceleration there, constrain the way this V enters in physical quantities, in amplitudes. So for instance, if you consider an amplitude where you have, for some reason, I quark going out and J quark, so let me do it in the same way. Let's say that you have an amplitude like the ones that you have when in meson mixing physics, where you have the down quark J going in, down quark K going out, and here you have something like dl and dm. By exchanging W's, we can generate transitions like this, which only involve down-type quarks, and these are obtained by exchanging the W. Well, then you know that this amplitude, which mixes all the flavor, because now you see I, J, K, L, these are all different. If I change the phases of this amplitude is not invariant, okay? So, but this amplitude should therefore transform precisely. So this amplitude will be a function of this Vij, because it's coming from integrating out the computing diagrams in this theory, and it will have to have a dependence on the Vij precisely to match the transformation properties of the external legs. And that is simply to tell you that this will go like Vik star Vij, V n m star, and V and L. Okay, so you may have some, no, what did I do? Yes, okay, yes, exactly. And if you write it this way, sorry, I'm writing really crappily. Let me write it this way here. So this way, there's going to be some I that you have to add in, and this compensates, and this is like that, and then this is VNM star, VNL, okay? And then if you look at what this is, well, look, you know how this comes about. This is exchanging W's, okay? But, and here precisely you have the 4 vertices where at each vertex you have a V, and the V that you get there, and whether it's V or V star, is precisely matched by this symmetry, okay? Again, this is a triviality, okay? But it's simply to tell you that the way that symmetries, even simple symmetries like this, are useful and are relevant in telling you how a certain quantity depends on the parameters. Now, in general, in the Lagrangian, you have many more contribution to an amplitude like this, okay? And so, because in quantum mechanics, as you know, everything is a superposition of amplitudes. But integral language, going from here to there, is the probability amplitude for that to happen amounts is obtained by considering all the possible ways that can happen, and this is summing over all the amplitudes. And each of these amplitudes, if you want, if you can view it in this discretized way, will have to depend on the physical parameter of your system in such a way as to match simple transformation properties like these ones, okay? Satisfying this selection rules. And it is in this situation that the notion of natural and unnatural arises, okay? So the notion of natural and unnatural arises precisely when considering selection rules. By the way, very much like in the standard model, you can rescale the fields, okay? You can change the phase of the fields and change the V, like in this way. In gravity, for instance, you can rescale the metric and change what is the parameter. The metric is a field, everything is a field, and I can rescale the metric. So what is the parameter that transforms in that case? Well, it's all the dimensionful parameter transform. Okay? So you can apply similar things in other situations, okay? So in that case, it's really massive to get rescale. And then again, that is useful to see how these parameters enter into physical quantities. So but let me give you now the main notion I wanted to, okay, here. So what I give here, the things I said are trivial, okay, they're absolutely trivial, but it was necessary to remind them, okay. No, we use them since the very beginning. So what I want to emphasize is that the ideas that are behind this are the very first idea you familiarized with in physics. Things like dimensional analysis. So what is dimensional analysis? Dimensional analysis is the thing I just told you, is covariance of your equations under change of units. Okay? And it's just in the same class as covariant under rotations, covariant under rephasing of the core fields, and several others. So now here comes, after having recalled this notion, I'm now ready to give you the general definition of natural and unnatural, okay? So, statement is this, let's stick to a quantum system, okay? I think it's nice to think it this way. In a quantum system, any observable is going to be like an amplitude, okay? And in fact, in the standard model where you compute, for instance, flavor transitions, it's precisely like that. You get many different contributions to the low energy scattering amplitude. And they are associated to different parameters, okay? So in quantum mechanics or in quantum field theory, an observable can be written as the sum of different amplitude, which I characterize by the index, I don't know, alpha. So in the two-slit experiment, there are two amplitudes, okay? But when you compute some meson decays, you have a few amplitudes, okay? So you have amplitudes. And now, this amplitude will, like all things I've showed so far, or even this quantity, this amplitude could be some part of an amplitude. So for instance, in a two-point function, you can think about the mass, okay, which is associated with the two-point function of a field, okay. So it's going to be the sum of several contributions, okay, but very much like in everything else, the left-hand side and the right-hand side will transform in the same way under all possible symmetries you can think of, which is to say under all possible transformations of the dynamical variable and the parameters that leave the action invariant. Okay, so these are clearly not, the vast majority of them are not symmetry because the parameters transform, but they're still useful because the relation between what you observe and what you compute has to respect this transformation. Has to transform in the same way. And now each of this amplitude, formally, you can think of it as being some expression. You can think of a monomial in general, like in the simplest case, it's just a monomial of all the couplings that you have, of all the couplings that you have in your system. Okay, so let me say it this way. Maybe I should say lambda 1, lambda n. Okay, these are all your couplings. Okay, with coefficients that are not changeable in the theory. Okay, remember you have the Lagrangian, you have the couplings, and you compute things. And this is a calculable coefficient. If you may compute it, and if you're lazy, it's something there. Okay. Normally, you can think of this as a numerical coefficient. So formally, this is order 1. Okay, it's not something that you can change. In certain coupling, you may be able to make it. You may be allowed to make it small or large, but it is just a coefficient. And now, what can we say of this? Okay, we have various contributions, and then we look at the result. Okay, we look at the result in the face of all the several contributions, which we are able to compute. Okay, and the result could be either we really look at the result numerically. Okay, we just compute each of these, and when we sum it up, maybe there's an integral. Okay, it could be more complicated, and we look at the result of the computer. Okay, or we do an experiment. Okay, we do the computation, and then there is an experiment. And there are okay. So there can arise, okay, a situation where what you get here, okay, that if you want the size of this result, okay, the size of this amplitude is much smaller than the size of the maximum of all these amplitudes. Take these amplitudes and take the biggest one, okay, or one of the biggest, the biggest or the second, or yeah, the biggest one, okay, and it could be a situation where the result is much less than that. Okay? If that is the case, it means that this biggest contribution cannot be the only big one. There must be some other contribution that compensates. Okay, the result. Okay, and in this situation, okay, two things are you can think can happen. Okay, there could be two reasons why this happens. The first reason, number one, well, we have missed one symmetry, some symmetry. in the sense that there are some of these contributions are related to one another by symmetry. There may be a symmetry that tells us that one contribution is minus the other. In that sense, they should be considered together because the symmetry relates. Okay, so and it often happens that when you compute things and you get something much smaller than the individual, you say, oh, but we have missed a symmetry, and you go back and you find it. This, and then after you take that symmetry into account, and you organize your contribution in a way that really respects the symmetry, then it may happen that there's no such mystery like that. In other words, that the result you get is of the order of the biggest of the suitably constructed contributions, okay? And in reality, and you check again, and you see that with more care, in other words, by collecting together the individual contribution, in other words, if two amplitudes are related by symmetry, then by symmetry in a sense even exact, then you should group them together. Okay, they are part of the same contribution. Okay, they're not independent. Okay, and okay, it could happen that we missed something, but careful analysis implies that if you do it carefully, the size of the result is of the order of the maximum of these amplitudes. When that is the case, we call the situation natural. A natural situation is one where if you're lazy and you do estimates only using symmetries and putting order one coefficient, you more or less get the right result, or the right order of magnitude. Okay? So the natural situation is where it's very much like with the pendulum. Okay, with dimensionality, we're able to figure out that the frequency is square root of g over L. Okay, and then you go and do the and then you solve exactly the system. You see that it's square root of 2L with a number of order 1. Good, that's the natural situation. Okay, same thing for the atom. If the function f is of order 1, well, that's a natural situation, and so on and so forth. Okay, so that's what we have. That's the situation where the selection. In other words, this is a situation where the selection rules are sufficient to infer the result. 2, instead, we did not miss. Any extra symmetry. Okay, and indeed, there is a conspiracy of terms in the sum which cannot in any way be viewed as the consequence of symmetry, that still manage to cancel the final result and give you a very small result. Okay? And this situation here is a situation where we say it's a fine-tuned situation. It's a situation where our first estimate as crappy physicists, where the lazy physicists who don't want to do any detailed computation of the coefficients, where our estimate of the result based on that fails completely. Okay? And a situation like that, we call it unnatural. In the sense that the natural situation is a situation where the expectation, the naive expectation of selection rules is blatantly violated by a clever organization of the various contributions that cannot be understood by any symmetry. Now, notice that both situations are possible. There's nothing terribly wrong with this, okay, at least in the sense of computations, okay, in the sense of, but that's certainly a very special situation, okay? And well, this is the more typical one. And it turns out that, I mean, an example, and to understand how typical or untypical this situation where you have a natural combination of parameters, okay, like the one I'm depicting here, where some quantity turns out to be much smaller than what you would expect based on selection rules is precisely the one that you have in the systems that I was mentioning before, in the condensed matter systems where, which are in the neighborhood of a phase transition, okay? And rather than insisting on that, turns out that all these systems, at least the laboratory, if we stick to laboratory, okay, if we, in our understanding of laboratory physics, a situation where these accidents or this apparently accident arise when there is a great variety of possibilities. In other words, where imagine there are very many systems of the same type, okay, and in any of these systems we can compute an amplitude like this, okay. Imagine we have many of them, okay, we construct, so this is some amplitude in some condensed matter system which we can construct by putting together some things, okay? But there is a big family of systems like that we can construct, okay? And in any element, in any member of this family, we will have a result like this, only that the couplings here are different, okay? The coefficient may even be the same, but the couplings are different because we constructed it's essentially the same system constructed with slightly different original rules that makes the couplings different, okay? And well, it's clear that if this family is big enough, there is the possibility for finding examples or elements in this family, I mean, members of this family where big cancellation like the one I'm saying here can happen, okay? So in other words, in order to have a situation where we have an unnatural or two quantity, normally that situation arises when we have what we call a landscape of possibility. It seems like that these two things are, or call it variety, of systems, this in this way, or if you want a landscape of systems. And let me give you an example of that, okay? Let me give you the example I show when I teach this class. An example of that is, for instance, there are this, it's called a thallium copper chloride. It's a crystal that behaves, you can find this in a paper by Sachdel. It's also in this book. This is a system that behaves like an antiferromagnet. Okay, it's an antiferromagnet, but it has two phases of behavior, and the different phases are controlled by the pressure. Now, let me explain. So what you have, so what you want to consider here is some effective description for the dynamics of the magnetization, okay? In fact, this is an antiferromagnet, so what you consider is not the magnetization, but what is called the staggered magnetization. It doesn't matter, okay? Not important what it is, it's just that this quantity, the staggered magnetization, behaves like a scalar triplet under rotations, okay? It's just, it's something like an SO3 triplet, like the SO3 triplet of an ordinary scalar field theory, okay? So you have this lattice, okay, where you have the sides, okay, and this lattice you can put it in a vise, okay, where you exert the force. You can compress it, okay, you just crank the vise, okay, and so one property of crystals, okay, is that they can exist in a range of pressures. Okay? You take a square crystal, you put it in a vise, and you start cranking, and for some time in your cranking, this thing doesn't break. At a certain point, it will break. Okay, but there is a range. There's a continuum range, which is a variety or a landscape of pressure, where this thing stays there and is still a crystal, and you can. And for different values of these continuous values of P, you can study the system. In particular study, it's some equivalent of an amplitude, okay? So this cranking up the pressure is equivalent to constructing a variety of systems, where now the couplings that describe the Lagrangian are functions of the pressure. Is this clear? Okay, so so these guys in this matter they really behave like a god, okay? They can construct quantum field theories, okay, in this way, okay? But we have the advantage that we cannot, so we have this real advantage that we cannot play Go. Okay. We are given one, we are more fundamentalists. They are like pagans, okay? They have all sorts of quantum field. We have one, okay? We have one, just given one. So, okay. That is what makes us different. Of course, they're having much more fun, they're bacchanalia, they're doing things. Oh, we have a new system. And we're always sad, we're always, that's very different between paganism and monotheism, but it's okay. So there is this thing, and imagining there is a way that survives some, as soon as there is some separation of scales, in a sense, I'm already assuming to have done some tuning. But let's say we've already done some separation of scales. Let's say there is the lattice length is 1, and the fluctuations happen have a mass which is like 10 times that. We haven't done a little bit. I'm just going back to our lattice friend there. Okay, I've done, so at that point you have the right to start writing a continuum Lagrangian. Okay, the continuum Lagrangian would be something like what? Well, d phi. Okay. This is call it the kinetic term, okay? Actually, this is you don't have Poincare invariance. So the time derivative and the space derivative don't have the same coefficient, but never mind, okay? You have a kinetic term, but what matters for me is the potential, okay? And then of course you have all other terms. But the potential is crucial. The potential consists, it's a rotational invariant, okay? So there's going to be a quadratic term plus a quartic term. And of course, there are all higher order terms, but again, by the same story, if there is even the beginning of a separation of scales, all the other guys have higher dimensions. You can forget them in first approximation, you can focus on these two guys. Now, these two guys are both functions of pressure in general, okay? And pressure is a continuum parameter, okay? This is an amazing property of crystals, okay? Crystals are amazing for that. Alberto is probably one of the few people in the world who understands this thing. Of this.
I don't think I am. Thank you, I don't think I am.
Oh, I thought you were the only one. Anyway, at least it's the one who emphasizes to me. Okay, it's the only guy I know. Okay. And shit, I did not. Oh, I dropped an example. Fuck. It's okay. I'll do it later. Okay. And I really dropped another example of. It's okay. Okay. Well. In this situation, okay, you can, what happens is that when you have a function of one parameter, what happens generically? What does a function of one parameter do in physics, generically? Crosses zero, right? It may not cross zero, but generically, a function of one parameter has no reason to be positive, and this one has more reason than that, okay? If let's say that this is positive, then this controls the behavior of the field far away, then this guy has a right to become negative, okay? And so it turns out that in this particular system, for some reasonable pressure in the middle of some pressure range, this actually crosses zero, okay? And so close to that point, you can expand this as essentially m0 squared, 1 minus p critical, something like that. They describe it roughly like that. So what is that is happening here? I'm writing this silly formula like this. This m0 here, square, is the quadratic term, call it the master, that if you were clever enough, if you are a good condensed matter theorist, you can deduce what this m0 is precisely with dimensional analysis. Okay, but with the basic dimensional analysis, you can deduce this M0 from atomic physics. It's going to be something that depends on alpha and M electron. That's it. Okay, it just depends on the relevant and the number of. There's going to be some integer properties having to do with the type of atom you have there. But atomic physics allows you to compute this M0 purely in terms of the fundamental parameter of atomic physics, which are the electron mass. So you can compute it. And you would expect this to be of this order. However, there is this family of systems that your guy, the guy with the vice, that appears also in some mafia movies, that does something with the vice, okay, can stretch this thing to the point where the result, naive result of your dimensional analysis and selection rules fails completely, and this thing is zero. Okay? So this is the typical situation, at least in laboratory research. I'm not talking about the universe because I don't understand the universe, but in laboratory research, the occurrence of extreme cancellation of this type, which are not enforced by the symmetry, is always associated to the existence of a variety of choices. Okay? To the existence, there are many ways there are many incarnations of this system, and therefore we can get that. Okay. Now, this is essentially in condensed matter, where they have the freedom to behave like gods. They are like, and having a lab technician who can sit there the whole day, trying to change the pressure and find the place where this cancels. We, in particle physics, we don't have that option, okay? We don't have that option, and because we don't think there is a lab technician behind fundamental physics. Maybe there is, maybe it would be very sad. We're like fish in an aquarium in a condensed matter experiment happening on the scale of the universe, and there's somebody cranking things to tune things. But let's assume that is not the case, okay? And so this fact has led Toft, I think also others already at the time, in the late 70s, to introduce the notion of naturalness, okay? The notion that, I mean, when we consider fundamental theories, we should, I mean, if we don't, in other words, if we bar, so the notion that natural, that fundamental physics is expected not to have this type of accidents, okay? And so therefore it should fall into this other class. Okay? Now, of course, there is the option that, yeah, also we are in a landscape, okay, and that there could be many choices, okay? But that's are essentially the two possibilities I think that we understand sort of at this time, okay? The natural one, and the natural one is associated with the existence of a landscape. Now, I had another example that I wanted to show typical of particle physics, okay? And I should have shown it before this one. If you give me 5 minutes, I can do it, okay? Is that doable? Oh, you don't give me 5 minutes, okay? I can do it tomorrow, okay? You guys, tell me. Should I go? Okay. So, so this is the situation of, as concerns the computation of what looks like a scalar mass in condensed matter. We have situations, and this does not, and this follows what I just said, okay? The question is, do we have situations where we can do, where we can test this notion in, how does this notion work in situations that we know, okay? Now, the situation that we know is QCD, okay? And there are two basic examples in QCD where you could think in these terms and you end up in this situation, okay? And it's important to know them, okay? Now, of these two situations, one was even crucial to determine the existence of a new particle, the charm core, okay? And I like to very quickly discuss that, but I think it's gonna take more, it's gonna take 15 minutes. So, just for tomorrow, okay, I forgot, before presenting this, I should have presented QCD as the example of where this thing here is realized without the existence of a landscape. But I will do it tomorrow, I think it's better.
by